welcome to Monday. Okay, as always on Monday, we have Alex do this evening. On Wednesday, we will have mini exam 2. It will cover all of today's material. We should. The plan is to get through all of limiting reactant. Limiting reactants is on next week's Alex objectives because that's how objectives work. So that means if you would like to use Alex as a practice tool, you're going to need to finish today's and start next week's before Wednesday. Mini exam 2 will be on Wednesday. It covers all of those things. So lectures 5 through 8 are from 2 weeks ago when we have mini exam 1 through all the way to today. That's on there. Any questions about the announcements? I do want to remind everyone, because I feel like someone will go home and have a panic. Maybe you won't have a panic. Maybe you will. This is your exam periodic table. It just doesn't have the names. Since it's kind of hard to see on there. As you can see, it has the atomic number at the top, element symbol, molar mass, everything you need to know. Questions about the mini exam other than how many questions, because I haven't even started a Word document? Yeah?
So for the periodic table, we just need to know the compound's name?
So you'll need to be able to go both ways. So if I give you FeCl2 or iron 2 chloride. Oh, I really thought that was going to go in. It was going to be like this beautiful moment for myself, but it didn't. So I need you to go either way. If I give you the formula to the name or the name to the formula, that's all I'm asking you to do, including the polyatomics. You don't need to memorize the mass, the atomic numbers, where it is on the periodic table. That's it. Yeah?
You won't give us any of the elements from like the 57 to 71, 89, 103.
If I do, it will say like, shoot, I don't know what's down there, but if I did, it would say, using radium, Ra, it would give you more context clues than just nothing. So if I use them, you'll get more than just something else. Other questions? So as you start to prepare for that, a couple of things. One, SI tomorrow night will run from 6 to 8. It is on Zoom. She is running some version of a practice mini exam too. I don't really know what that will look like. So if you can go for some, I would recommend it. If you can go for all, that would be fantastic. If you can only go for a half an hour, that's great. If SI doesn't work for you, I have office hours tomorrow from 4:30 to 5:30 on Zoom, and Wednesday from 12 to 2, also on Zoom. You can come. I will work problems. I will explain concepts. Today, several people showed up with the Alex questions. Yeah?
Will the SI on Zoom be recorded? Because I can't make it.
As far as I know, none of them are recorded these days. But there are other options for you. So there is tutoring. Hold on. That was in. Well, no one can read this, but we can. So there is tutoring if you were like, can't make that. So these are the different chemistry courses. Today you could go to tutoring directly after class, which is located in the library at the fountains. There is a Zoom walk-in, which I think basically means click that link and go into something. For the most part, all of the tutors are really excellent. Most of them have to get approved. I've signed off on lots of the tutors. Like, did they pass your class, yes or no? So you should get someone who can, in fact, answer a chemistry question. Should is always the operative word on that, just so we're clear. Questions? How are we feeling about mini exam 2? Okay. I'll try to make jokes today. Feels like they're going to go kind of flat. But I am not afraid. I mean, I'm a little afraid because it makes me feel like we're back in the Zoom days where it's just like me by myself. I'm not going to lie, I think I'm pretty clever. All right. Any questions about any of the previous material, balancing equations, empirical formula, yada yadas? Fantastic. So, balanced chemical equations. A balanced chemical equation is a recipe. It is a recipe for how you will get, I don't want to say the right answer, but it's going to tell you how much product you could make. So, a balanced equation provides a ratio of reactants to products. This is going to allow us to estimate, I'm going to also say / calculate the products or the reactants. One way that we can think about this is if you open the back of the, if you read the back of the chocolate chip bag, it has a recipe, right? It tells you if you add 2 sticks of butter, 3/4 of a cup of white sugar, 3/4 of a cup of brown sugar, and all the rest of it, it says you should get 5½ dozen cookies. Maybe 4½. Either way, the reality is when I bake cookies, apparently I like big cookies, so I never get the amount that they predict. But when I mix all the ingredients, as long as I follow the recipe, I get the same amount of cookie dough. It's just that I make bigger cookies where I guess think your cookies should be like the size of like a very large grape, and that's not how I roll in my life. So the reality is this balanced equation is just the recipe for how to get to chocolate chip cookies. Now, chocolate chip cookies have like millions of ingredients in terms of chemical reactions. But if you were thinking about a brownie mix, like the kind that you went to the grocery and you bought and it says, add water, add oil, add eggs. If you wanted to change that and make more or less, you could do it in that ratio, right? If it called for 3 eggs and you only had 1 egg, you would somehow need to weigh out and divide the chocolate mix into a third. So this balanced reaction is just going to give you that information. So as chemists, what we want to be able to do is to say, I started with 10 grams of this. How much are we going to get at the end? So last week, we talked about converting grams to moles, right? Take the grams, divide by the molar mass. Now we have moles. So today, we're going to take that, and we're going to continue to build on that into new and different ways. So using this balanced chemical equation of 2H2 plus O2 gas, all gases, gives you 2H2 gas. So it says how many moles of water are produced if we start with 1.57 moles of water. Nope, oxygen, sorry. So I'm going to take my 1.57 moles of O2, and now I need to convert to moles of water. But oxygen and water are not the same. But these stoichiometric coefficients are going to allow us to allow us to convert from one to the other. So we know that 1 mole of O2 is equal to 2 moles of H2O. This is the stoichiometric ratio. When you plug this into your calculator, you should hopefully get 3.14 moles of H2O. All we did is convert from moles to moles using the stoichiometric ratio. The stoichiometric ratio is just the big numbers at the front of a balanced chemical equation. What questions do we have about doing this calculation using the stoichiometric ratio? Yeah.
So I know Alex, it was saying about the avocado number. Is this the same as that, or is that completely different?
So Avogadro's number is when you want to go to atoms or molecules. In this case, we're just starting with moles and going to moles. Usually, Avogadro's number and balanced chemical equations are not part of the same calculation. I'd like to say usually because I don't usually ask that way, but we know how Alex likes to feel sometimes. So in this case, basically what we would see, I would never ask you for Avogadro's number using a balanced chemical equation. I could imagine because that Alex would say, if you started with 9 million hydrogen gas atoms, how much would you get? And then you could use it. But otherwise, no. Good question. Any other questions? So the second part asks, what if we started with 25 grams of H2? So we're going to take our 25.0 grams of H2, and in order to get to the moles of water, we need to convert grams of H2 into moles of H2. In 1 mole of H2, there is 2.02 grams of H2. For every 2 moles of H2, there are 2 moles of H2O. Who can give me an answer for this calculation? If you don't have your calculator out, I might suggest getting it out. So the 2.02 on the bottom is the molecular weight of hydrogen gas. Because hydrogen gas is diatomic, so 1.01 times 2 allows you to determine the molecular weight of that. Did you say 12.87?
No, 12.3.
Just 12.4 moles of H2O. Questions about this calculation?
I'm sorry, can you repeat what the 2.02 grams of H2 is?
Yeah. So this 2.02 grams of H2 is the molecular weight of H2. So we go from grams, we want to convert to moles. We're going to use molecular weight here. Then we want to convert to moles. This is going to use the stoichiometric ratio here. It is not present in this calculation, but literally in the next one I'm going to show you. We're going to go from moles back to grams, use the other molecular weight. Just so that we can draw our roadmap to refer back to on the next one. So this is that there's 2.02 grams per mole of H2. I just put it on the bottom to convert to moles. Fantastic question. Other questions? Yeah?
What is the 2 moles of H2O over 2 moles of H2 for?
Well, in this case, it cancels out to be 1. But in the previous calculation, 2 moles of H2 to every 1 mole of water is an important part.
O2. Yeah. Okay. So it depends on the problem. All right.
Right. So you need to use the stoichiometric ratio to allow you to compare moles of item A to moles of item B
Oh, yeah.
using the balanced chemical equation.
All right. I get it.
It's okay. Good question. Other questions? So, not shockingly, we're going to upgrade ourselves just a little here. So we have a balanced chemical equation, and it asks what mass in grams of CO2 is produced from 1 gram of butane. So I like to think of these as the grams to moles, moles to moles, moles to grams calculations. We want to go from grams of reactant to, in this case, grams of product. So in this case, we need to convert grams of butane to moles of butane. So we're going to take our 1.00 grams of C4H10, and it is 58.14 grams in 1 mole of C4H10. Now we have the moles of butane. From here, we want to convert that to CO2 using the stoichiometric ratio. So for every 2 moles of C4H10, we get 8 moles of CO2. 1 mole of CO2 is 44.01 grams of CO2. Now you can plug this into your calculator. You should get 3.03 grams. So about at this point in the semester, people start having calculator, I don't want to call them issues, because that really downplays what's happening. What really happens is we don't know how to approach this, because now we've got a whole string of numbers that we're trying to put into our calculator. Students can approach this one of several ways. If it was me, I would take 1, divide by 58.14, hit enter. Multiply by 8, enter. Divide by 2, enter. Multiply by 44.01. That'll give you 3.03. If what you really realize is you really hate doing all the entering and all that, your other option will be to take 1.00 times 1 times 8 times 44.01. This is going to give you some answer. Then you can also do 58.14 times 2 times 1, and this gives you that answer. So this will be step 1, step 2, step 3 is to take the square and divide it by the triangle. I did not plug these into my calculator, so I cannot tell you what those answers are. If you're interested, I will obviously do that real fast. But what I'm trying to show you is that there are different ways for you to use this equation to get that answer. You could do this way, or you could just plug it in however you like. Questions? Yeah?
We don't have to write it out like that, right?
Like this?
The top one.
What would you have written instead?
1 divided by 50, whatever the...
58.14.
And then I would do divided by 2 times 8 times 44.
So, you don't have to write it out exactly like this, but if you don't get the right answer in your work and I can't follow it, then it's much harder for me to give you partial credit.
What if I labeled them? Like if I wrote down
Like these?
like if I wrote down 58.14 and then I wrote molar mass of methane.
on the next one, when I give you guys a second, I'll come look at it. Because you may be saying things, but I cannot picture what you've written, and so I don't want to make you do extra work. Other questions? Yeah?
Where did 58.14 and 44.01 come from?
These are the molecular weights. So this is 4 times 12.01 plus 10 times 1.01. Should give you 58. And CO2 is 12.01 plus 2 times 16.00. They're just the molar masses. Great questions. Other questions? Yeah?
Whenever you're going from grams to moles, do you not like multiply by a coefficient?
Down here. So the question is, when you calculate the molar mass, do you not take into account the coefficients? I don't. I have seen people do this. I don't. I take into account the coefficients here. So if you were to multiply this by 2, this whole part would become irrelevant. I find that people often, keeping track of the molar masses and trying to figure out when you need a 2 and when you need an 8, makes some people, it would make me go crazy. So what I prefer and what I strongly recommend is that you use grams to mole using the molar mass, then use the stoichiometric coefficient to go from moles of one to moles of the other, as opposed to saying, I can't really do like high math in my head. So like 8 times 44, like 350-ish, give or take. It's probably not close at all. But the point is, I think it makes it more clear to do it using the stoichiometric coefficients. Yeah.
But if we do it the other way on like the quiz and we get it wrong, we still be able to give us partial credit if we put like 8 then parentheses 44.01 and then 2 parentheses 58.14.
So the question is, if we do it a different way and we get it wrong, can we still get partial credit? That's hard for me to know today. It is always my goal to give you the maximum amount of partial credit. But if you start deviating from the plan, it's hard for me to tell where you have a plan and where you just vomited a bunch of numbers on the page and kind of hope that they ended up in the right arrangement.
All right, I'll probably try and do it that way then.
I would strongly recommend this way, only because this will always get you to the right answer, or mostly get you to the right answer. Other questions? How many of you feel, when I throw up the next example, really whether or not you feel like it or not, in this one, I'm going to give you 4.5. I'm going to give you all the way to 5. I can't see the clock, but I have a watch on. So, using the balanced chemical equation, hydrofluoric acid cannot be stored in glass bottles because the silicates in the glass are attacked by HF. If there's 0.45 grams of sodium silicate in a glass bottle, how many grams of HF will dissolve the silicates in the bottle? 2 informational data points. 1, this is hydrofluoric acid. This is sodium silicate. This is a fully balanced equation. We are looking at a reactant to reactant calculation. I'm not going to say I'm going to wander around, but I'm going to be here. If you have a question, your goal is to have an answer. You can go like that if you like if you said 5 by 2 moles of whatever. I think you can do that. was a lot easier in the old days, in person, so I could just say, push this button.
What's happening right now? Hi. Is the mini exam happening right now? I'm sorry.
No, it's on Wednesday.
Okay.
We're just solving problems.
Okay.
I
Right.
was just back here instead of up there.
Great. Is there anywhere to be? Because I am soaking wet right now. It seems like there are certain areas you prefer me to not get water on.
I personally don't care where you sit, but you are very damp, and so your classmates may prefer that you don't. You are welcome to sit anywhere you'd like. Maybe just not on top of someone.
I will not be so graciously rude.
There are seats back over here on the edge if you'd like.
very big number. It's not.
It's 0.45 grams. Nope. Yeah.
No, that's not what I got. I got 90.
Okay. Well, I hear a lot of, wait a minute, it's only reactants to reactants? Yes. So in this case, what we're looking at, putting my handy dandy laser pointer, is the ratio of sodium silicate to 8 moles of HF. So, most of you, what I saw was, okay, we're moving in the right direction. So, I'm going to erase all this. And so we're going to take our 0.45 grams of, in this case, sodium Na2SiO3. We're going to convert to moles using the molar mass, which is 122.07 grams in 1 mole of Na2SiO3. Now, from here, if you were to stop right here and do no more, that just gives you the moles of sodium silicate. Now, using the molar ratio, or the stoichiometric coefficients, for every 1 mole of Na2SiO3, you need 8 moles of HF. Now, 1 mole of HF is 20.01 grams of HF. So when you plug this in, you should hopefully get 0.59 grams of HF. So what questions do we have about this calculation? Yeah?
Did you get 8 moles over 1 mole because those are the coefficients?
That's correct.
Okay.
So the coefficients, I tend to call them the stoichiometric ratio.
Yeah.
Those are just the big numbers at the front.
Right.
It's just a different term for that.
Okay.
But yes, you're exactly correct. Other questions? Yeah?
Where did your 20.01 come from? I'm sorry, I kind of.
No. 20.01 is hopefully 1.01 plus 19. That gives you 20.01. The molar mass of fluorine is like 18.999, which rounds to 19.
So what I realized I did wrong is when I was doing the molecular weight, I multiplied by 8 as well. Because I thought the essence that 8 was a brand that means there's 8 hydrogens and 8 fluorines. But why is that not the case?
So the question is, if you multiply this by 8, so let's think about, so what is the role of this part?
Transition?
Yeah, it's going to give you a transition, but we transition using the stoichiometric ratio. So you used the stoichiometric ratio, and then you used it again.
Okay, that makes sense.
Because here, you had, 200, give or take?
It was 160.
Okay, 160 something. But did you put it per 1 mole of HF or per 8 moles?
8.
So did you also have this part? So if you wanted to, I would strongly encourage you not to. You could have put 160 over 8 moles of HF and included this part. Yeah, it's a lot of extra work. You could just use the stoichiometric ratio and then the molecular weight of whatever you're looking at, and that will give you the ability to convert between them. It's a fair question. It's a frequent question. Other questions that we have. Well, let's do another example, y'all. I know. So in this case, solid lithium hydroxide is used to remove carbon dioxide exhaled by astronauts in space. Lithium hydroxide, no. The lithium hydroxide reacts with carbon dioxide to form solid lithium carbonate and liquid water. How many grams of lithium hydroxide are required if 250 grams of carbon dioxide is exhaled by the astronauts? What is step 1? We need an equation. Let's start with that. So in this case, I'm going to leave this up, but I'm going to write the equation. So we have lithium hydroxide, solid, plus CO2, gas, gives us lithium carbonate, 2 CO3 solid, plus water vapor. Is this equation balanced? I feel like I heard some maybes. No. Where can I start with the balancing of this equation?
Wouldn't H2O be G because it's vaporized? Or with water vapor? Instead of L?
It creates liquid water.
Oh, I thought you said.
It's okay. A 2 in front of the lithium hydroxide. Are we now balanced? How many of you feel like you could acquire the right answer if I give you 4 minutes? How many of you could set up the whole thing in 4 minutes? Set it up, but come back to calculating the molecular weight. Set up all the rest of it. Yes. It's like a lot of thunder. Usually you can't hear anything in here. At least I hope that's thunder. Sounds like I'm starting to see some correct answers. So in this case, we're going to take our 250.0 grams of CO2 multiplied by the inverse of the molecular weight, 44.01 grams in 1 mole of CO2. 1 mole of CO2 gives you 2 moles of lithium hydroxide, and 1 mole of lithium hydroxide weighs 23.95 grams, which gives you 272.097 grams. When we use our significant figures, we get 272.1 grams. What questions do we have about this calculation? I'm seeing a lot of excited faces that we got the right answer, which is what I like to see. So, now we're going to start talking about limiting reactants. So, what we want to start to think about, thus far we've said, if we have this much CO2, how much of this do we need? Or if we had moles of sodium silicate, how much HF do we need? We could also have said, if I had 25 grams of 250 grams of CO2, how much water did we make? Hopefully all of you feel, I don't want to say confident, relatively confident, newly confident in your ability using any mass and a balanced chemical equation to convert to any other participant in the reaction. I'm seeing a little terrified faces. I'd like to report I feel confident in your abilities. Are you confident?
Well, just to clarify, what we just did is reactant to reactant.
Yes.
And will it always be like that when we're using the balance?
No. So you could, with the same technique, convert from any one participant to any other participant in the reaction. So often in the past, so this is an old exam question of mine, I think. Maybe it has been on A-graded assessment at some point in my career. So in this case, we have the ability, I could have also asked you about anything else. So now what we want to start to think about is if we have 2 reactants, or not 2 products, but 2 reactants, because we're going to start to think about limiting reactants. Now, usually limiting reactants strikes terror in the heart of Gen Chem 1 students. Maybe you've heard it's super hard. Maybe by the end of today, you're going to be like, I never want to think about this again. I'd like to postulate that for most of us, we already think about limiting reactants. We just don't think about it in terms of a chemical reaction. Good, nice. So a limiting reactant is going to tell us what is going to run out first. If we were to think about grilled cheese sandwiches. Now, these are traditional grilled cheese. You get 2 slices of bread, some American cheese, butter or mayonnaise. That's not going to be part of this. You're going to fry it. If you would like to discuss the validity of butter versus mayo, we can talk about that after class. I'm a butter person in the South, in Louisiana. People like to put mayo on the outside. It crisps up real nice. It is pretty disgusting, but delicious. Now, back to where I was attempting to go before. So, 2 slices of bread, which are salad, plus 1 cheese, also salad. We're going to add a little heat, and that's going to give you 1 grilled cheese. So we have that's salad. We have a balanced chemical equation. You came to my house. I have 2/3 of a loaf of bread. I have 21 slices. And I only have an 8-pack of cheese. How many sandwiches can I make? 8. We've all done limiting reactants now, right? That's all we're asking. A limiting reactant is the one that runs out first. Now, there are many ways to think about limiting reactants. Likely what you did in your head was you said, okay, this requires 16 slices of bread. This would require 10 and a half slices of cheese. Therefore, I can only make 8. For a chemical equation, we'll be able to take our 21 breads. Now we're going to use our stoichiometric ratio of 2 bread to 1 cheese to get 10.5 cheeses. I know, 8 cheese, 1 cheese to 2 breads. That tells you 16 breads. This is what we have. This is what we need to use all we have. So at this point, we can say we need 16 slices of bread, or we need 10 and a half slices of cheese. If I asked you how many slices of bread were left in the bag, provided you made all the sandwiches you could, you would have said 21 minus 16 equals 5 slices. This is your excess. So let me ask you a question. If I used all 8 slices of cheese, how much cheese is left over?
0.
Big fat 0. When we think about excess reagent or limiting reagent, the limiting reagent is all used up. This is the thing that you use the most of, and it's all gone. By default, the amount of excess, or the amount of the limiting reactant left over is 0, because it limits how much product you can make. What questions do we have here before obviously we're going to move into some chemical equations here in like 10 seconds. What questions do we have thus far? Yeah?
If you give us the amount of grams from one of the reactants and not the other, is it given that that's all in the reactant?
Yes. So if you are provided, like in the previous section where you only get one value, by default, maybe default's not the right word. Yeah, by default, that is the limiting reactant. Alex and myself will say things like, if I gave you 16 slices of bread and excess cheese, it feels weird. Basically, in that case, I will try to tell you what is the limiting reactant without using those words, because they will be scary.
So the limiting reactant is when you don't have enough of?
Yeah.
So would it be cheese in this case?
Cheese is the limiting reactant. So in this example, where we are going to go back to our production of water, 2 moles of H2 plus 1 mole of O2 gives you 2 H2O. If we start the reaction with 10 moles of H2 and 7 moles of O2, what is the limiting reactant? Yes. So we're going to take our 10 moles of H2, react 2 moles of H2, gives you 1 mole of O2, and that's going to give you 5 moles of O2, or you can take your 7 moles of O2, 1 mole of O2 to 2 moles of H2, and that's going to give you 14 moles of H2. So I do these calculations. It is more than likely true that if you took high school chemistry or intro to chem or any other place where you've learned this, likely you just converted your H2 to H2O and your O2 to H2O, and the one that makes the least product is the limiting reactant. That's totally true. That will give you the right answer. If the question is asking, what is the limiting reactant? Which it is. But this part of how much of the excess remains is not part of that calculation. So in this case, the H2 being the limiting reactant is true. So H2 is limiting because we're going to run out of it first. So the excess is the amount of H2 that we, or the O2 that we started with, 7 moles of O2 minus 5 moles of O2, which gives you 2 moles of O2. Questions about this calculation? Yeah.
So since there is a 2 before the H2 and a 2 before the H2, wouldn't that imply that you can only react with positive number of moles?
Can you say that again?
Because the 2 is there before the H2, and the 2 is there before the H2O, it kind of implies that you can only react with a positive number of moles, right? Like you only have 2 sets of H2 going in at the same time.
Yes.
Well,
Well,
I'm confusing myself at this point.
I'm not saying that you're confusing me, but I'm not sure that you're thinking about this in the way that I would think about this.
No, I'm definitely confusing myself. I feel like I understand it now that I've said it out loud, actually.
Okay.
Sorry.
No, it's totally okay. Yeah.
How do you know which one's the limiting? Is it the one that when you do the calculation has the biggest amount of moles?
So this is what you have. This is what you need.
Oh.
So in order to use up all of this, you have to have 5 moles of oxygen. Alternatively, 7 moles of oxygen requires that you have 14 moles of hydrogen. You don't have this many because you only have 10, which tells you that it's the limiting reactant.
Oh, so if the starting number of moles of H2O and then the end number of moles of H2O, if the starting number is smaller than the end number, then it's a limiting reactant.
So that's 2 different calculations. So this,
I know, but I mean, like,
if you compare this number to this number,
yeah, that's what I'm saying.
yes, the lower number here is the limiting number of reactants. Or no, the limiting reactant. Other questions? Yeah.
So, wait, why did you use the numbers that you use in the access?
So in the problem, it tells us that we have 7 moles of O2, right? In order to use up all of the H2, how many moles of oxygen gas are we going to use?
7.
5.
Oh.
So this is a perfectly balanced arrangement. If we think about our cheese arrangement here, it's the place where 2 breads plus 1 cheese makes a sandwich. In this case, if we use up all the cheese, we know that there's leftover bread. So I'm asking you how much of whatever is left over is left over. Other questions? I do want to be clear. You could have done this calculation and answered all the rest of my questions. You don't have to do the second part. This will make more sense as we continue to move on. But I will always try to show you as much work as possible. Because if there's 2 reactants, 50% of you will choose one, 50% of you would choose the other as your starting point calculation. So let's look at a more exacting example. So to make LEDs, molten gallium reacts with arsenic to make gallium arsenide. If 4 grams of gallium reacts with 5.5 grams of arsenic, what is the limiting reactant? How much of the excess is left? And how many grams of gallium arsenide is produced? I'll do this one. Just kind of guide us all through this adventure together. On the next one, we will all get an opportunity to do it together. Well, you will do it, then I will do it. We'll move on that way. So the first step here is we need a balanced chemical equation. So gallium, molten means liquid, plus arsenic, which is a solid, gives us solid gallium arsenide. And luckily, this equation is balanced as soon as we wrote it on the board. So now we have 4 grams of gallium and 5.5 grams of arsenic. More than likely on a mini exam or the exam or final or anything else, you would just pick one and kind of cross your fingers. I'm going to show you both. So we're going to take our 4.00 grams of gallium that I'm going to convert using the molecular weight of 69.72 grams and 1 mole of gallium. 1 mole of gallium gives you 1 mole of arsenic, and 1 mole of arsenic is 74.92 grams, and that equals 4.80 grams of arsenic. So from here, to use all of the gallium, we need 4.3 grams of arsenic. We could stop here, because we know the way this works is that if you have this much and you need this much, and this is less than what you have, this has to be your limiting reactant. However, if you were the other 50% and you had started with 5.5 grams of arsenic, it is 74.92 grams, 1 mole of arsenic, 1 mole of arsenic, 1 mole of gallium, 1 mole of gallium is 69.72 grams, and that equals 5.12 grams of gallium. So regardless of which one you chose, whether you started reactant to reactant, gallium to arsenic, or arsenic to gallium, we can determine the limiting reactant. In this case, what is the limiting reactant? You have a 50-50 shot. These are like way better than lotto odds. You just, if nothing else, just pick one with confidence. Gallium, see? So gallium is in fact the limiting reactant. So the way we got there is that 4 grams of gallium requires 4.3 grams of arsenic. We started with 5.5 grams of arsenic. So we know that we would have enough. If we were to think about using up all of the arsenic, you would have to have 5.12 grams of gallium, but you only have 4 grams. This means that you need more than you have. So gallium is the limiting reactant. The excess arsenic is 5.50 grams minus 4.30 grams, and that gives you 1.20 grams of arsenic. From here, it asks one last question: how many grams of gallium arsenide is produced? So we're going to take our 4.00 grams of gallium, using the molar mass of 69.72 grams and 1 mole of gallium. 1 mole of gallium plus there's 1 mole of gallium arsenide. 1 mole of gallium arsenide weighs 144.64 grams, which gives us 8.30 grams of gallium arsenide. Now, as we marinate in all of this information, what questions do we have about these calculations? Yeah?
Could you just add the gallium you have to the arsenic that you use?
Yes, but that will never work on an exam.
Oh,
It should, it won't. Mostly because we're going to start to use more complex things, and that assumes that you have to do It works on this one. I promise it doesn't work on the rest to determine the product. Other questions? We all feel confident in this technique? We all feel like this is the worst? Yeah.
So the last calculation with the 8.3, why is it 1 mole of gallium arsenide combined?
Here?
Yes.
Because it's asking you to calculate the,
Access.
this one here is asking you to calculate the product. It's okay, so in the question, it asks you 3 different things. I would likely make you fill out a table so you're not like hoping for the best, because I like tables. Also, Alex will make you fill out tables on tables on tables. So, next, a scientist mixes together 3.05 grams of titanium metal with 6 grams of chlorine gas to form liquid titanium 4 chloride. What is the limiting reactant? How much product will be formed? How much of the excess reagent is left? I'm going to give you the balanced chemical equation. I'm going to leave off all this work so you can use it as a template. We have titanium solid plus chlorine gas gives you titanium 4 chloride liquid. Yep. So this equation is not balanced. We need a 2 in front of the chlorine gas. Using this information, see what you can do. The short answer to both of those is yes. Sometimes it will say in the question. If this was an exam question, it would be like this. A, write the balanced chemical equation, including all states. B, calculate something else. It shouldn't, or it will say using the following balanced equation, using the unbalanced equation. I will try not to make it a guessing game. It is never my goal to trick people. I feel like that's a common misconception. Or maybe an experience in other places. Yes. Yes. But not by 4.
Yeah, because, and then I use the
Yes, something like that.
So if you were given these questions, this one's just to follow as soon as we did this one, you don't have to do it.
This is CO2, and you have the 1 molarness because you made it into 1 mole of chlorine. So this should be 70 pounds. Yes. What?
And that's from, so now go to
Otherwise, what you have was totally correct. Because you only have chlorine as a singular atom into this diatomic chlorine, which otherwise, yeah. Yes.
And then is the focus more this, or is it? Would it be split? This?
It would be that. How's it coming? It's a lot of fun. Yeah. So you definitely can do them as moles and do all the calculations in multiple. You don't want to know how many moles you started with. So if it's telling you that you have 0.13 moles, I'm not going to go that far, but if you don't know how many moles you have. All right. So, in the interest of making sure that you guys depart here with an actual answer, I'm going to go ahead and start solving this. So I'm basically going to recreate all of the work that I did that I'm now erasing, but with a new chemical equation. So I'm going to start with 3.05 grams of titanium for the sole reason that is the first number in the equation. You may choose the other, you may pick anything you like. So we're going to take our 3.05 grams of titanium, using the molar mass of 47.88 grams in 1 mole. We know that 1 mole of titanium is equivalent to 2 moles of Cl2. 1 mole of Cl2 weighs 70.97 grams because there are 2 chlorines, it's diatomic. And that gives you 9.04 grams of Cl2.
I thought they had coefficient. Oh, wait, never mind.
It's the fact that it's chlorine gas that's a diatomic.
All right.
So from here, we have 9.04 grams of chlorine gas. That right there tells us that chlorine gas is the limiting reactant. So the first question is, what is the limiting reactant? Check. It then asks us how much product will be formed. So I'm going to take my chlorine gas, which is 6.00 grams of Cl2, 70.90 grams of Cl2, and 1 mole of Cl2, 2 moles of Cl2, plus 1 mole of titanium chloride, 1 mole of titanium Cl4, which is 189.68 grams. That gives you 8.03 grams of titanium chloride. So we've answered 2 out of the 3 questions. The third one is about the excess reagent is left. So in this case, if we want to know how much chlorine is left and how much of the titanium is left, in order to determine the amount of titanium, we need to know how much would be used. So we're going to take our 6.00 grams of chlorine gas, divide by the molar mass of 70.9 grams of Cl2 in 1 mole, Cl2, which gives us 2 moles of Cl2 for every 1 mole of titanium. 1 mole of titanium is 47.88 grams, and that gives you 2.03 grams of titanium. So, how much titanium is left? We're going to subtract what we started with, which is 3.05 grams. Nope, not plussing. Minus 2.03 grams. And that's going to give you 1.02 grams of titanium. How much chlorine gas is left? None. If it is the limiting reactant, it's all gone. It's like a tray of cookies where the good cookies are gone. They are fully eaten. What questions do we have? So limiting reactants will be on the mini exam. The next slide starts to talk about percent yield. So on Wednesday, we will continue to talk about limiting reactants, but it's just up until this point, just so we're all pretty clear on how far you need to study. If you have questions, feel free to pop down. If you don't, I will see you on Wednesday.